Hello, hello. I will work on this problem. It's a little bit too long to be at a final exam, for example, but because I make you work on it, I will show you how to solve this. So I will use P equal 200 Newton on both sides. And I will use the diameter of the wire, the little d, equal 15 millimeter. All the dimensions are millimeter, so that's what I will use. Okay, so the first steps will be to split this object into different parts, okay, all the parts that are mobile together. So let me use some color. I will make a free body diagram of, I will put everything on the right, of the lower handle, this one. Like this. I have a point B. I have the point C that is aligned like this. And I have, let's call that P. I have the little CD road there. And this was interesting because you can see right away that it is a two forces member. Okay. And I will make the upper, this one, the upper blade. I know a little bit where I want to go. So I will not draw what I don't need. Okay, there. So I have the point D. I have the point A. And I have the connection with the wire there. Okay, let's call that N. Why I did this? Because let's draw some forces now. Forces that we know. We need to have at least one of those parts who have a force that we know. And what we know is the P equal 200 Newton there. That is perfectly vertical. P equal 200 Newton. And the force that we don't know, we have this force N1. And that's the force that we try to find. At A, we have a pin connection, so we have two forces. And D and C, that's where it's interesting. D and C. So if we look at the bottom one, the green part, at B, we have two forces. If we do the moment about B, we can see that the force P will make a moment in that direction, so the force C needs to do a moment in that direction. So meaning we need to have the force FCD going down. This one will go up, FCD, going down, always the same, and going up, FCD, this one. Okay, so we have all our forces. The only force that we know is the force. I should make it blue. Let me make it blue. Oops, this one should be blue. The only force that we know is the force P, 200 Newton, and all the other forces we don't know. But if we begin by doing on the green part, the sum of the moment about B equals 0, we can solve for FCD. And if we do number 2, we use the purple part and we do sum of the moment about A equals 0. We know FCD, we can solve for N1. Okay. The only thing that we need is some dimensions and angle. So let's look at this there. We need to have the distance BC. So we have the distance BC already there. So we have the 24, this one. But we also need the distance from B to P, this one. How we can find this one? We can use, okay, we can use the 50. We can use the 190. And we can remove the 24. That makes sense? So, and we need to find this distance there. So one important distance that we need to find right now, I will make it in orange, is this one. So let's find this distance. Yes, so I will draw a little triangle. So we have A, O, and B. Okay, we can make a triangle like this with a right angle. We have 20 and 20, so this distance total A to B is 40, and this angle there is the same than the 20 there, so it's 20 degrees. So the little distance that I will call this little distance A. Let me see if I call this the same way. Yes, I call this little distance A. We can write that sine of 20 degrees, it's equal to the opposite A divided by 40. So we have A equal 40 divided by sine 20 degrees. That give us A equal 13 times 7 millimeter. Not time, point. 13.7 millimeter. Okay, so we know that this one equals 13.7. So we can find this distance that will be 190 minus 13.7. That is 176.3 millimeter. So now we have this distance on this free body diagram. Let me draw it. 176.3 millimeter. So the 24, the 166. Now what we are missing, the last thing that we are missing is this angle there with x. Okay, because if we look, oops, A and B are aligned, so we just need that angle there. So to find that angle, not super difficult because we already have, let me clean this. Oops, we already have the 50. We have now the 13.7, we have the 24, and we have this 25. So what we get is like, we have D, we have C, we have this distance 25, and this little distance there that I call B. What is this distance B? This distance there, B, okay, smaller than that. Oops, B. We will have, let me use some green. So everything that I will do about this distance, B will be in green, okay? We have B, that is equal to 50 minus 13.7 and minus 24. So we can write that B equal 12.3 millimeter. So this is this distance, and why we need B? We need B to find this angle alpha, okay? So now we have B that is equal to 12.3 millimeter. So we have the angle alpha, that is tangent alpha, equal opposite 25 divided by 12.3. So we got alpha, that is equal to 63.8 degrees. Oops. So now that we have this angle, we can come back on this free body diagram and using 63.8 degrees there. Okay, we are ready to work on our equation number 1. Let's work on equation number 1. Okay, equation number 1. I will make it next to this free body diagram. So equation number 1, sum of the moment about B. So we have FCD going in the negative directions. We want to take only the vertical component because the horizontal component is going through B, so it doesn't create any moment. So we need just the vertical component, so it's the opposite of the angle. So it's sine 63.8 degrees time the distance 24. Don't forget the distance, time this distance. And P will be plus P time the total distance 176.3 that we found before equals 0. Okay, and P, so you have FCD that's equal to P, that is 200 for our example, divided by 176.3 and divided by 24 times sine of 63.8 degrees. We got the FCD equal to 1,638 Newton. first steps done. Oops, with the green free-body diagram, we get this FCD. Okay, we did half of the work. So we know FCD, we know FCD. We can now change this FCD on the purple free-body diagram blue, because we know that value, that's the same. So let me draw the FCD there. And we also know the angle alpha, that is 63.8 degrees. Try to get some space. Oops, in blue, FCD. Okay, let's look at this part there in purple a little bit more. So we are looking at this one. Okay, something that we have to notice is like the point A is not aligned with the point D, vertically or horizontally. So let me change this one a little bit to make it a little bit higher. Okay, this point A, I will even exaggerate a little bit so we don't make the mistake. At the point A, and we have our two unknown, like this. Okay, so when we will do the moment about A, we need some distance. Okay, we need this horizontal distance, we have it. So we have this distance 50. But we also need this vertical distance, so this one. Okay, so we will need to work on that. And for N1, okay, we will need that distance that I call C. So I will draw that distance there, that what we call C. And let me call that last distance there D. I call D the diameter, so we call this one E. Okay, so how do we get that distance? We need to find this distance. This distance there. So I am on that one. So we have 25. We have we know the 25. We can find this total distance there. We already have it. We already have it. We already have the triangle. So that this one. And yeah, that will be this. So let's do. I will work in blue to get this distance E. Okay, we'll work on this distance E. So we have the point A, we have the point B, we have the point C, and we have the point D, like this. We know that this distance, we know that this distance is 25. And we will need to find this distance. Okay, and to find this distance, we use the same triangle. So 40 and 20 degrees. But that time, we will use cosine 20 degrees. It's equal to the value that we are looking for, x, divided by 40. So x just look at the equal 40 times cosine 20 degrees. Okay. What is this distance? Let me check. Oh, this is 37. So x equals 37.6 millimeter. Okay. And now, to find E there, I'm looking for this distance E. So we will have x that is equal to 25 plus E. So we can find E that is equal to 37.6 minus 25. So we got a dimension E of 12.6 millimeter. 12.6 millimeter. So we can add this distance on this Fibonacci diagram. That's the distance E. Let me remove E and write 12.6 millimeter. That's at the point D. Okay. And now we need this distance C. Here on the right, we need this distance C. So to find this distance C, let's go back on this one. Okay. I will clean. So we are looking to find this distance C. Okay. And this distance C will depend on the diameter. That's the only time that it will depend on the diameter. So we have the diameter D. Okay. And we have the 20 degrees inside this one. So let me draw that. We have like this, and this. Be careful, the square angles is there. We have this distance D, in our case, that is 15, and we have a 20 degrees angle, and the distance that we are looking for is this C. So we have tangent 20 degrees, that is equal to 15 divided by C. We can write that C equal 15 divided by tangent 20 degrees. So C, in our case, will be 38.5. Okay? So we can come back on our Fibonacci diagram and write that C equals 38.5. And one last thing is, like, we will not use N1, but we can use the complement that is perpendicular to 38.5 instead. And we know that this angle there will be also 20 degrees. Oops. Okay, because that's the same angle between this one and the vertical, that's the same angle that this one. Okay, of the 90, etc. So I think we got all our dimension. Let's do this. Yes, we have all our dimension. So number 2, I will do the moment. So this one was the sum of the moment about B equals 0. And the step number 2 is the sum of the moment about A equals 0. Okay. So what we have? We have the FCD sine 63.8. That is the vertical complement, times 50, this distance, that creates rotations in the positive direction. After that, we have plus FCD cosine 63.8 degrees. So this is this little horizontal one that also creates a positive rotation. But we need to multiply by 12.6 degrees, 12.6 millimeter. So time 12.6. And for N1, so N1 will create a negative rotation, so that will be minus N1. So we want this complement, so cosine 20 degrees, and time the distance 38.5. And it's equal to 0. So we can write that N1 will be equal to, so in the bottom we divide it by cosine 20 degrees and time 38.5. So I should put at least parentheses there. And on the top, we will have the distance 50 sine 63.5, 63.8, and plus 12.6 time cosine 63.5, so 63.8 degrees too. And that will give us the N1 that is equal to 2,285 Newton. And that's the answer that we get with the free body diagram number 2. I should almost say number 3 because we use also the little blue parts, the two two forces member. And the conclusion is like from a P force of 200 Newton, we apply a normal force on the wire of 2,285 Newton. So we multiply by more than 10, 11, multiplied by 11. The force with this special scissor there, just with the shape, actually not the shape, but the location of the different pin connections and the number of parts and the way it's made, we multiply by 10, the forces. So let me make a little summary. And I draw one thing that I want to tell you on the wire. So I have the wire like this, okay? And I draw two normal force, perpendicular and perpendicular. But if we leave it like this way, it will slip to the right. So we will need to add some friction forces that are always perpendicular to the normal force this way to balance, to keep it static. Okay. Yeah, that's what we need to add, the friction forces there. We will work on that later. So little summary, what we did, little overview. We went from one big complex structure, machine, to a few free body diagrams, but well chosen, with at least one with a known value, a given value, never more than 3 unknown. And if you have like 3 unknown, I mean 3 connections. And if you have a pin connections, you take the moment at the pin connection. Always worth it. So you ended up being just one unknown, because there's 2 unknown at the pin connections and 1 unknown left. And you solve with an equation of moment. Look for two forces member, because you know the directions of the two forces member. So we found the CD road with two forces member. And after that, you just go one step at a time. And what took some time is to find all those little dimensions for this problem. That was a little bit challenging. That was the challenge there. And we ended up solving out two equation of moment. So that is for this problem. You see, it was not that crazy, but we need to take the time and very well analyze the different dimension. Let me clean that before I turn off the video. Thank you if you are still there, and if you have listened until that very last moment. Thank you for watching. Bye-bye.